Okay, Professor, if you agree, we can start. Okay. Good afternoon, everyone, and welcome to this lecture. Today we have Professor Kohayakawa as an invited speaker. It is great pleasure to introduce Professor. Kohayakawa got his PhD degree in 1991 from Cambridge University, supervised by Bolobash, and at the moment is a full professor at the Institute of Mathematics and Statistics of the University of Sao Paulo. He works mainly in the areas of combinatorics and discrete mathematics and also probability theory. Today, a professor is going to speak about arithmetic progression in sumsets and in subsetsums of sparse random sets, which is related to the extremal and additive combinatorics. So now we are eager to hear Kohayakawa and invite him to start the talk, please.
Thank you very much. So thank you very much to the organizers of the lectures. It's a great pleasure for me to be able to speak in this series. Thank you very much to everybody who is attending. I realized that the abstract of the talk was somewhat technical. I'm happy that you came nevertheless. Right, so I will talk about this one kind of problem in arithmetic combinatorics. And actually it will be more probabilistic than just a purely extremal additive combinatorics. There will be a strong probabilistic component. Okay, so the plan is that the plan is that I will give an introduction to the topic. It will be somewhat long, just to kind of set the scene. I imagine that maybe this subject is far away from your main interests, so I thought I would speak more about the background. So I will talk about arithmetic progressions in just sets of integers and also in sumsets. My main topic will be sumsets. I will say what sumsets are in a short while. I will be interested in studying threshold functions. And again, so threshold functions are important topics. I mean, a main topic of study in probabilistic combinatorics, but I will again introduce them in a short while. Then I will be able to, after this longer introduction, I will be able to state the results, the main results of this talk. There will be kind of two kinds of results. One will be about just arithmetic progressions in sumsets. And then later, I will not only consider pure sumsets, I will consider sumsets when you take subsets of random sets. But anyway, when it comes, I will explain what I mean by those things. I will maybe say something about the proofs, but probably since the introduction is longer and the statement of the results are somewhat technical, maybe there won't be so much time for proofs. But perhaps I can say something. Right, so I hope this talk, the general, I will try to explain everything from the beginning. So if you see definitions or terms that don't make sense, please feel free to interrupt me and ask. Right, so the new results in this talk are together with Rafael Miyazaki. So he was a master student here in Sao Paulo. He's now a PhD student at Emory University. The second set of results are with Marcelo Campos, who is at Cambridge at the moment, but will be at IMPA in Rio de Janeiro from next year. And Gabriel Daya, who is a PhD student of Rob Morris at IMPA. Right, so let me start this longish introduction. So first of all, I will be interested in sets of integers. I will have a finite universe, so I will have the integers typically from 1 to n. So this my notation brackets n for the first n positive integers. We will be interested in considering subsets of brackets n. So you see these red points are the elements of this set A. Typically, we can think of A in two ways. Maybe A was chosen by some adversary who is trying to kind of being nasty to us, or maybe A will be a random set. Anyway, these will be the contexts, the kinds of sets A that we will consider. And within the set A, maybe we are interested in finding arithmetic progression. So for instance, you see in the bottom picture, a 4-term arithmetic progression, right? So integers which are equally spaced, and I have 4 of them. And my notation for such progressions will be AP4, so 4-element arithmetic progression. Okay, so this is some old paper of Erdős and Turan. So this is from 1936, as you see in the bottom. So let's read just the beginning. So in this paper, they consider sequences of integers, so A1, A2, and so on, up to some big N. And the restriction on the set of integers is that they should not contain 3 terms of an arithmetic, 3 terms AI, AL, AS, such that AI minus AL is equal to AL minus AS. In other words, these 3 A's form a progression on 3 elements, right? Okay, and of course the restriction is that these numbers are at most n. And at the bottom, you see, we consider those with the maximum number of elements and denote by R of n, the number of such elements that you can have in such a 3AP3 set. So yeah, just to make sure this is the main kind of important thing. So we have capital N, and we're interested in finding within the first positive capital N natural numbers some sequence of elements or some subset of elements such that you do not have an AP3, 3 terms forming an arithmetic progression. And let R of n be the maximal number, the maximal cardinality of such a set. So later in this paper, Erdős and Turan prove that for any epsilon, this function R of n is at most some constant 4/9 plus epsilon times n, if n is bigger than some n0, which depends on epsilon. In other words, you get kind of density 4/9 for such a set. Later, they say at present, this is the best bound, the best result for R of n, and they claim, they say that it's probable that R of n is actually some vanishing proportion of n, so little o of n. This was proved sometimes later by Klaus Roth in 1953, in fact, and this was the first result of a very rich area of research. And I will not really discuss the developments. I will just say that kind of the main theorem, the best known theorem in this area is Semiradis theorem, which generalizes Roth's theorem to progressions of arbitrary length. So let's define Rk of n. So I have now little n, they had big N, but I have little n. So Rk of little n to be the maximal size cardinality of a set S contained in the first positive n integers, which contains no APK, no k element arithmetic progression. So previously we were considering R3 of n. So again, APK means k-term arithmetic progression. Right, so Semiradis theorem states that this function Rk of n is like as you see, for any fixed k and any epsilon, if n0 is large enough, or there is some constant n0, such that for any n bigger or equal n0, it is true that Rk of n is at most epsilon times n. So such a set S, as you see in the definition of Rk of n, free of APKs, can have density at most epsilon, as long as your universe, brackets n, is big enough. Another way of saying this is that this function Rk of n is little o of n. Right, so as mentioned before, and as many of you, I'm sure know, this is the kind of beginning, it's a major theorem of a very rich area of research, which I will not really go into so much. Now, it will be convenient for me to state Semiramis theorem just slightly differently. So I stated Semiramis theorem by saying that Rk of n is little o of n, but we can say it in the slightly different way as you see now. So we fix k again, and now we think of an adversary picking some alpha density set or subset of brackets n. So alpha, you can think of it as constant. So we have k, some integer, alpha, some small constant, 1/10 or something like that. Well, for any k and epsilon, there's some n0, such that if n is bigger than n0, then any set A in brackets n, which has at least alpha n elements, is guaranteed to contain an APK. So any set of density alpha or more must contain an APK as long as the universe is bigger than n0. So that's another way of stating Semiramis theorem. And it will be convenient for me to define this function L. So given some set of integers A, L of A just means the largest K for which A contains an APK. So Semiramis theorem, as you see here, states that the set A of density alpha, or at least alpha, is such that L of A is at least K. Now you can ask what kind of numerical relation there is, or what you can say about this this quantity k, right? The way it's stated, the theorem as stated, is something like, well, k goes to infinity as n goes to infinity. That is the kind of thing that you can read out from the way the theorem is stated right now. But you can ask how fast k goes to infinity with n. And as it turns out, Semiramis theorem, or his proof, gives a bound, but the bound is quite small. For instance, because he uses what later became known as Semiramis regularity lemma. And in the regularity lemma, the numbers, the numerical kind of quantities that arise are either grow very fast or are very small. Anyway, so you get something like the bound that you get on k perhaps is something like log star of n. So log star is something like number of times you have to iterate the log function so that n becomes less than 1. Anyway, so k grows to infinity, but not so fast. I mean, quite small, quite slowly. And so much later, kind of 2000, Gauss gave a completely different proof of Semiramis theorem, and he got much better numerical bounds. So from his results, you can kind of read that k goes to infinity as maybe 5 times iterated logarithm of n. It's still quite small, right? So it's log n or something like that. But that's kind of the best you can do. So if you have some set A which is chosen by some adversary, the only thing that he promises is to pick some density alpha set, then you cannot really say much more than that. And the point is that when you consider Sumsets, which I will define in a moment, you get much longer progressions. So let's move on. So given some set A of integers, capital A plus A is what you see there, is the set of pairwise sums of elements of big A. So little a plus little a prime, where A and A prime are in your given set big A. Perhaps sometimes I will write 2 times A, but I usually write A plus A. So A plus A just means pairwise sums. A prime could be equal to A, you allow that. So this is a bit like a Minkowski sum in geometry. Anyway, you take all pairwise sums. And if you consider pairwise sums, it turns out that the progressions that you can find in such sets is much bigger as you see in this theorem of Green. So this theorem is strengthening of a previous theorem of Jean Bourgain. He had a bound, so the bound you see here in expression 2 is exponential of root log n, ignoring constants. He had maybe cube root of log n. But anyway, so this is the much bigger lower bound that you can give for arithmetic progressions in sumsets. But let me kind of say something about these sumsets, and to do that, let me move here. So when you talk about sumsets, so I could have, let's say I have a set A, and this set A, suppose you already know that, suppose you know that A and B belong to this set A, well, and you consider A plus A. Of course, when you consider A plus A, this just the two elements A, B give rise to A plus A. So, I mean, you translate everything by A, right? So you have A and B translated by A. So you add A. So this is a translation by A. But of course, when you consider A plus A, you also translate everything by B. So of course, you also get A translated by B. And of course, you get also B translated by B. So B plus B plus plus. Well, okay, then you see, so this gap is B minus A. You get now a progression on 3 elements with the same gap B minus A. So just by having 2 elements, you automatically get an AP3. So you see, the A plus A is a set which has a lot of additive structure. Well, this is just a kind of a little remark that makes kind of easier to understand why you are expected to get progressions which are much longer. And now this function, as you see there, this exponential of log, it's kind of a, let me see again, so let me do this. So the expression you see here, right? So what is it? So ignoring constants, this is e to the root log n, root log n. Well, this is less than n to epsilon, a lot less than n to the epsilon, and a lot bigger than, I don't know, so log n raised to any power, right? So this is some function which is more than any polynomial, any power of log n, but it's not quite polynomial in n. Right. So this is some function between kind of these two types of growth. By the way, I will use this later also. When I write less like this, I mean that when you take the quotient, yeah, so just to make sure, so f is less g. That means that when I divide f by g, this goes to 0 as n goes to infinity. Anyway, they have different orders of growth, right? So this statement, I mean, expression number 2, so this lower bound that you see, tells us that when you consider sumsets, well, maybe I should read this theorem with you. So now I have some set A, non-empty, and let's say the set A has density alpha. So alpha is size of A divided by n. So alpha shows up here in this bound. Well, I think you can ignore this log n. So the main point is that you have a function of the form e to the alpha root log n. C that shows that is here is just some absolute constant. Anyway, so the progression has size super polynomial, yeah, so log to any power, much more than log to any power, even though it's not quite a polynomial in n. So that is kind of this expression here on the right. So that is what you get when you consider progressions in some sets. It's really much bigger than if you just consider the set A. Of course, the set A here is chosen by an adversary, but the point is that A plus A has much more structure. Okay, so this is Green's theorem. Now, we'll be considering much sparser sets. I'm sorry, let me go back one page. So here, I think, in this theorem, alpha is not necessarily a constant. So you can plug in any set A with vanishing density. So you would be allowed to take some set A which has size A divided by log n or something like that, n divided by log n or something. This expression would still be bigger than 1, so it would be meaningful. But it's clear that if you take some alpha here, which is quite small, so let's say n divided, so alpha is 1 over log n, this becomes a trivial bound because the right-hand side of this becomes 1 or something, or less than 1. Anyway, so Green's theorem doesn't tell you much if you are interested in sets A, which are sparse. So for that reason, it's a natural question. So what happens if A is quite a sparse set? Can you say anything about progressions in A plus A? So let me talk about that now. So progressions in some sets of sparse sets. So here's a theorem of Kroot, Ruja, and Schoen, which gives you such a bound. So the bound here, as you see in 3, we are allowed to take sets A, which are powers of n, and the power is less than 1. So for instance, we could take this theorem for k equals 5. Yeah, for some technical reason, k has to be an odd integer here, so maybe k is 5. So then the lower bound in 3 would be 1 minus 1 over 4, so that means n raised to 3/4. It's a much sparser set, for which Green's theorem wouldn't say anything. But still, you can say that A plus A contains an AP 5. Now, if you want to have an AP, let's say 100, so a much longer progression, what you would have to do is to choose, you would see that the set A, to guarantee such a thing, the power of n in 3 would have to be something like 1 minus 1 over 99. Okay, it's supposed to be some odd integer, I said. So maybe k has to be 101. Right, so it would be, the exponent of n would be 1 minus 1 over 100, so 0.99. Anyway, it would be less than 1, but still would be close to 1. So this is what this theorem can deliver. And actually, of course, the numerical dependence is not quite right, but qualitatively, it is right. So there is some upper bound construction in the same paper, which gives, I will not say stated. I mean, I actually even could. So there is some upper bound. So as you see in 21, you have some upper bound for L of A plus A, and this upper bound has, yeah, you see this theta on the right hand side of 21. And also you see that this theta shows up in the exponent of n, one line above. So A is at least n to the 1 minus theta. If you have that kind of A, you have an upper bound, which is just a function of theta. Anyway, so the numerical dependence is not quite the same, but there is some corresponding upper bound here, which is actually not bad. So it's a bit like you have a different power of k in the exponent in 3. Anyway, so this is what you can say about sparse sets. As we saw before, 3 is kind of a trivial case, k equals 3. K equals 5 is already non-trivial, but then the bound the lower bound you need on A is some power of n, which was 3/4 in the case of k equals 5. Now, this is when the adversary, some adversary, chooses A. We will be interested in the random case. But before I go to that, let me talk about something different. So let me talk about thresholds. And thresholds, at least in the kind of combinatorics world, came up in the study of random graphs. So Erdős and Rainey, late 50s and 60s, they wrote a kind of the papers that started the area of random graphs. They started some systematic study of random graphs. Here, I will be interested in the binomial random graph, which is sometimes denoted GNP. And maybe I should, just to make sure, say something about that. So let me move. Sorry, let me move here. Yeah. So let me move here. So let me just very quickly, this will not be so important. I will not so much talk about graphs, but let me talk about this object, this GNP. So GNP is like this. So you have some fixed vertex set on n elements. We might as well consider brackets n, so the integers from 1 to n. You have some other parameter in this GNP, this p, and p is supposed to be some number between 0 and 1. Strictly between 0 and 1 to have something non-trivial. They could be 0, could be 1. But anyway, so in this brackets n, the vertex set of GNP, we consider two vertices x and y, arbitrary two vertices x and y. And what we do is to add an edge with probability p. So you flip a coin with bias p, so probability p of coming up heads, and you put this edge between x and y if and only if your biased coin comes up heads. So this is some random object, and this is this GNP. So what Erdős and Rainey did was to study the structure of this random graph. And I will not talk about that, but I mean, I think that one of the major discoveries that they arrived at was this giant component. So they noticed that the structure of GNP changes drastically when this parameter P, as you see here, is around 1 over n. By the way, I didn't say that, but this function, this probability P of the edges, it makes sense to consider constant P, for instance, P equals 1/2. But for many problems, it makes more sense to consider P which changes with n, which varies with n. So P is a function of n. And what I just said something about this giant component. What they noticed is that the structure of this graph changes a lot when P kind of is about 1 over n. I will not this is not relevant for this talk, so I will not talk more about that. Let me move on and say that in these papers, they also realized something very interesting. So they noticed that several properties of random graphs kind of start to happen suddenly. In other words, they observed that that you can define things called threshold functions. So let me move back here. Right. So as you see, so let's say P is some monotone increasing property of graphs. So that means that you have a property of graphs such that it's increasing because if you add an edge to a graph that has property P, then the graph continues to have property P. So the property is not destroyed by adding edges. So an example like that is I have a graph. I can ask whether this graph contains a triangle. This is a monotone increasing property because if a graph has a triangle, if I add some other edge, of course, it continues to have a triangle. Another property which is also monotone increasing is of being connected. If you have a connected graph, and if I add an edge, it is still connected. And notice that when I mean add an edge, you cannot add vertices. So you just add edges to a fixed ground set of vertices. Anyway, right. So suppose you have such a property. For any such property, it makes sense to define the thing that I will say now, this threshold function, this P star of n. So P star of n is called a threshold function for this property P if the following holds. So we have this GNP, this random graph, and we can check whether GNP has property P or not. Of course, GNP is a random object, so this is depends on the sample, right? The concrete sample that you obtain by sampling GNP. So the fact whether GNP has property P or not is a probabilistic event, is a random event. So you can ask what the probability is. And you require of P star to be like this. If your edge probability P has order of growth less than P star, this limiting probability has to be 0. In other words, if you have a GNP with little n very large, for that kind of P, you don't have property P with a high probability. I mean, you don't have probability P with very high probability. The probability that you have P is very close to 0. In the limit is 0. So that's what you require on the one hand for P star. On the other hand, if P has order of growth bigger than P star, this limiting probability has to be 1. So in other words, P star is the kind of critical probability for your property of interest, big P. Now, so let me give some examples. The first example is kind of, anyway, it's okay. So let's say the property P is to contain a triangle. Then the threshold function for that is 1 over n. So you can prove that. Actually, it's maybe better. Okay, let me carry on. Another property is you can, instead of talking about triangles, you could talk about the cliques on 4 vertices, K4s. So the threshold function is some different functions, is n to the minus 2/3. Another one, so the property of being connected. So when is GNP connected? The answer is, if the probability P of your edges is asymptotically less than 1 over n times log n, then your graph is not connected. But if the probability P of your edges is more than 1 over n log n asymptotically, then the probability that your GNP is connected is close to 1. In the limit is 1. Now, so just to make sure, so let's see. So for instance, it makes sense, maybe it makes sense for us to look at this, n to the minus 2/3. So this is the edge probability. So if you remember, you take GNP, so you have a fixed set of vertices, every edge occurs with probability little p, right? Well, you have n choose 2 potential edges. So in this random graph, you expect to get n choose 2 times p edges. So ignoring constants, let's say I'll write, this is more or less equal, n squared p, right? And p is n to the minus 2/3. I'm sorry, so it's n2 times p minus 2/3. So this is n6 minus 2/4, right? So we are talking about, we are saying the following. You expect this random graph here to have something like n to the 4/3 edges when you have this kind of p, right? So maybe that is more concrete. So it's perhaps more concrete to think of a graph G, which has n vertices, right? And m edges, and this m in this case is of order n to the 4/3. So saying that containing a K4 has threshold function n to the minus 2/3 kind of says that if you take a random graph like this, so a graph on n vertices and n to the 4/3 edges, that is the kind of the cut point. That's the critical point for this property of containing a clique on 4 vertices. If you take a random graph, not with this many edges, but n to the 4/3 minus a little bit. So let me say, this is quite extreme, but it could be, this minus 0.001. Then you will not have a clique on 4 points. On the other hand, if you put plus here, you will have a clique on 4 points. That's kind of what it means. Oh, I'm sorry. This is what it means. This threshold function kind of pinpoints the critical number of edges where some property kind of start to become true. And what is interesting is that this is the transition between not containing a clique on 4 points and containing a clique of 4 points happens at a precise point in the number of edges or probability. So so P star is kind of well defined, but it's well defined up to multiplicative constants. Right. So that is what Erdős and Rényi discovered. So they discovered that properties of random graphs or properties of graphs tend to happen kind of suddenly. If the graph is not sparse, well, if the graph is sparse, then it doesn't. But as you increase the density, the property kind of suddenly start to occur with high probability. Now, they observed this for concrete properties, but it turns out that this is a general phenomenon. For every non-trivial monotone increasing property, you do have a threshold function. So there is a well-defined point in the edge density where the property becomes true with high probability. Now, so this is a theorem of Bolobash and Thomason, and it turns out this thing doesn't have to do with graphs. It's just a property. It's true in a very abstract setting. And to say that, I will so maybe move again. So I wrote 3 things here, but maybe let's focus here on the second. So the first one kind of is the first bullet point tries to say that this the Bolobash-Thomason theorem is true in a very general setup. But let me say in the setup that is interesting to us. I will be interested in this object brackets NP, and that is a random binomial subset of brackets n. Okay, so we have already encountered brackets n, this. Now I have some probability little p, so little p is some number between 0 and 1. And if I put p here, it just means the following. You consider your brackets n, your set, and for every element in brackets n, you flip a coin, a p-biased coin, so probability p of coming up heads. And if it does, then you select that element and put it in your p set. Anyway, so this is a random subset, which is chosen as I just described. And maybe you're interested in knowing whether this random set tends or does not tend to contain 3 elements forming an arithmetic progression. So that could be my property of interest. This property is monotone increasing. If I have some set which contains an AP3, of course, if I add an element, it still contains that AP3, right? So it's increasing. And Bolobash, and the theorem of Bolobash and Thomason does imply that this property of containing AP3s admits a threshold function. And in fact, the threshold function, so you can compute, it's actually easy. And it turns out to be what is written here, n to the minus 2/3. Actually, there is some heuristic to get threshold functions. This heuristic works in several cases, but it fails in some others. It works in this case. What you have to do is to compute some expectation. So you compute the expected number of AP3s in your random set. So you compute this expectation. This expectation is easy to compute. So again, ignoring constants, the number of potential progressions of length 3 that you have in brackets n is something like n squared. So you pick the first element, you pick the second, that defines the third element of your progression. So you can do that. So that means that you have 2 degrees of freedom. So that gives you n squared progressions, AP3s in brackets n. And to get some fixed AP3 in your set, you need 3 particular elements to be present in your set. So you do this. So the expectation is n squared p cubed. And as you see, this number here is exactly the point where this function, this expectation, right, either goes to 0 or infinity, depending on whether your little p is less than n to the minus 2/3 or more than n to the minus 2/3. That's exactly the cut point. And this heuristic kind of gives you at least some idea of why the threshold function for this property is n to the minus 2/3. So this is correct in this set. I mean, you can prove it. Actually, it's very simple to prove that if p is a lot less this number, n to the minus 2/3, then the probability that you have an AP3 goes to 0. But you have to do a little bit more work in the other statements. Well, the other statement is if p is a lot more than n to the minus 2/3, then with probability tending to 1, you do have AP3 in brackets np. Anyway, right. So this is about threshold functions. And now let me move on, and I will be able to state our results. So again, we are considering brackets n, first positive n integers. We consider brackets np, the binomial random subset of brackets n. Bias p means, every element is present with probability p in the random set, brackets np. And we're interested in things like a plus a, where a is some random set. So you sample your brackets np set, and you consider that set plus itself. We're interested in progressions in this set. Okay, so we can ask, what is the threshold function for the property that a plus a contains an APK? So the threshold function for L of a plus a is at least k. And our theorem is that, first theorem is that you can determine this threshold function. And the threshold function is, as you see, the main thing is 5. The 6 is kind of easy. So if you want an APK, your bias, your coin, has to come up heads with probability n to the minus 1/2 minus 1 over k. Actually, it has to have bias asymptotically bigger than this thing you see in 5. If it so happens that your p is less than that, then you don't have APK. If it's more than 5, then you have an APK. So the picture, the point.
What was the definition of a plus a? I forgot the definition of a plus a.
Okay, sure. That is definitely very important. A plus a is like this. So you have some set. A here, right? Now this a plus a is, you consider a plus a prime with a and a prime here. You take all pairwise sums.
No, define L of A plus. What is the
Oh,
L?
I'm sorry. Right. L of A plus A. L of A plus A is just max K such that
there exists APK.
APK is contained in A plus A.
Oh, sorry.
Right. Okay, good. Let me see. I think I now would like to, right. I would like to say something about this threshold. And to do that, let me come here. So maybe here is 1, here is n. This is a qualitative diagram. So this is root n. And so if you think of the powers of n, so this is n to the power 0, this is n to the power 1/2, n to the power 1. And in the theorem, we had some thresholds, and the thresholds were like this. Yes, so it was minus 1/2 minus 1/k, right? This was P. But if you have probability P and you select elements from brackets n, the number of elements you get is n times this. So in other words, what you expect, the number of elements you expect in your random set brackets np. So this expectation of the size is n times the probability. In other words, this is n to the power 1/2 minus 1/k, right? So in other words, you're talking about, so you have here brackets n, and you take some random subset here, brackets np, and the number of elements you have in this random set is root n minus, n to the minus, n to the 1/2 minus 1/k, right? So in other words, the sets that you get will have sizes, things like n raised to 1/2 minus 1/3. So that is n to the 1/6, right? So the power here is 1/6. Well, anyway, and then you kind of come close like this, right? So this is a gap of 1/3 and 1/4, 1/5, and so on. Anyway, so these exponents that you see in the threshold function, this minus 1/2 minus 1k, gives you that kind of cut points in this diagram. And in fact, so maybe it would make sense for me to say, so for instance, let me talk about this cut point. This cut point is 1/4. What you can say, what you can read out from the theorem is the following. If you are in this range, so to the right of n to the 1/4, you are likely to have AP4 in your set. If you are to the left of 1/4, you are unlikely to have AP4. That is what it means. So again, so for each of these cut points, so for instance, this one, to the right, you know that you have an APK, to the left, you don't. So you have it is well precisely defined which power of n you have at the critical kind of transition between APK and the next APK plus 1. Anyway, so this is kind of what you can read out from this theorem. So the result is, I would say, satisfactory for any fixed k. But in this theorem, k is a constant. You could ask what happens if you are interested in k's that grow with n. And also, yes, and also let me go back to this picture. So you see something is happening around this point, right? So as your random set have expected size approaching root n, something, yeah, you get longer progressions, and you could kind of try to study what happens in the neighborhood of root n, or neighborhood of the probability P1 over root n. So that is the next point. So I would like to talk about progressions when P is around n to the minus 1/2. So just look at 7, so the inequality. I will give some tables soon. And in the table, I will give lower bounds and upper bounds for L of A plus A. So M lower, little m lower bound, big M upper bound. And these lower bounds and upper bounds will depend on what kind of P we are talking about. So let me go on and show the table. So again, so this is about P, which is less than 1 over root n, but it's approaching 1 over root n. So if you remember the diagram, I mean, this diagram here, you're really approaching root n, right? So what happens in the vicinity of n to the 1/2 for the size, or minus 1 over n for the probability P. Okay, so here's the table. So for each row of this table, you have some P, some hypothesis on P. You have a lower bound and upper bound. And in the last column, you have the ratio between the upper bound and the lower bound. It's kind of a big thing. I will not kind of read each row here. Let's just look at row number 2, so the second row. On the last column, you see that the quotient between the upper bound and the lower bound approaches 1. It's kind of 1. That kind of says that for that P, we know matching upper and lower bounds for L of A plus A. Now, the kind of P we need to have matching upper and lower bounds is what you read on the first column in the second row. In other words, it's square root of 1 over n times log raised to some power that goes to infinity. Anyway, so you have to be bounded away from 1 over n in this kind of stronger sense. That's when we know, that's when we have matching upper and lower bounds. And if you read the column on the right, this ratio between upper and lower bounds kind of deviate as you have different ranges of little p. Let me not kind of go into details here. I'm kind of running out of time. So for instance, it would be very interesting, I think, to determine this quantity, L of A plus A, when P is precisely 1 over root n, or some small constant over n square root of, so the last 2 rows in this table. The upper bound and lower bound have kind of, the ratio is quite big. Right, so this is the kind of thing that we can prove in the vicinity of root n. Now, if you, oh, by the way, so let me go back. So this is the case in which P is less than 1 over root n. You can ask what happens when you jump the vicinity, you go to the right. So the P here now is a lot bigger than 1 over root n. And then again, it's even worse. I mean, we don't have really good ways of getting upper bounds. I mean, yeah, so the upper bound and lower bound are not so great. Anyway, so this is what we can do for L of A plus A. Now, unfortunately, I will not have much time to say more about subset sums, but let me try to explain what I mean by that. And maybe it would make sense to say this. Yes, to say it here. Right. So far, what we did was to investigate this thing where A is a random set. It's a pure random set. Now, and I didn't quite manage to explain it maybe well enough, but if you remember, the theorem of Krut, Ruzhin, and Schoen gave bounds for this quantity, but when A is chosen by the adversary, so he picks a very bad set for you just promises that Hayes has some size like root n. And then you want to give some lower bound for this, right? And maybe you remember A had to have size something like n to the 3/4 to guarantee an AP5. But if you think of the numbers that we got in the random setting, you get much larger numbers for this when A is random. This is natural. So if the adversary picks a random set, it's much better for us. Now, so perhaps you could think, well, then what we should investigate is not this L of A plus A for A random, but we should pick we should let some adversary pick some subset A prime of brackets n. Of course, he cannot choose any set. He has to choose some set of some given density. I don't know. He has to pick at least 50% of the random set. But we have to have some adversary there. It becomes much more difficult for us to bound this quantity from below because the adversary can be really nasty and pick some bad set within the random set. So another way of thinking is the following. So in Green's theorem, what you have is the following. You have some adversary who picks from brackets n. So you can think you have this ambient space brackets n. And the adversary picks just some alpha subset, which is as bad as possible. And we still have to prove bounds for A plus A, right? Now we do something slightly different. I mean, we do something different. We change this ambient space to this random set, and still the adversary has to pick some alpha fraction of this random set. What can we say about L of A prime plus A prime? Then it becomes kind of more difficult, and but still we have theorems for it, and I will finish by kind of just going through this. So this is like the theorem of Green, but then with this different ambient space. So we have a random sparsified ambient space. So let me show it here. So instead of having all of the brackets n, we have this random set. Now, the adversary has to pick some alpha proportion of this random set, and we can guarantee a lower bound on L of A prime plus A prime. What is the lower bound? The lower bound is this. And this lower bound is the same lower bound as you see in Green's theorem, except that the constant C that you see here is not quite the same, but it has the same format. So in other words, in Green's theorem, the promise is that you start with this set brackets n, the full set, but now you can sparsify it to brackets n p and still guarantee the same kind of bound for the progressions in your subset sum. Well, of course, this cannot be true for arbitrarily any p. You need some bound on p. And the bound on p is as you see here. Is as you see here. Is as you see here. The bound on p, the main term is this 1 over root n. And you have to be bounded away from 1 over root n by this power of log. So if you're to the right of that critical point, 1 over root n, as we saw in the diagram, you kind of get Green's theorem, even if you sparsify the ambient space. Right, I'm sorry. So this is becoming, this became more technical, but maybe this is the correct kind of analog. Of the random, it's the random version of Green's theorem. What is interesting is that the lower bound, the length of the progressions that you can guarantee in this A prime plus A prime is the same as in Green's theorem, but that's not because we give a different proof of Green's theorem. We kind of adapt some proof of Green's theorem itself. We prove some kind of robust version of Green's theorem using some known proof. of that. Right, so I will not be able to say anything more than this or about the proof or anything. So let me just, yeah, so there would be some stuff to say, but let me just move on. And thank you very much for your attention.
Thank you very much for your nice talk. Okay, so we have 5 minutes time for questions. If any questions, please. Any question? Any questions? Okay, so let me to check the chat box. Any questions? Okay, it seems that there is no question. So let me to end this meeting by thanking Professor Kohayakawa again for accepting our invitation, and also let me to thanks the audience of this meeting for participation today. I hope to see you in the future in another combinatorics lecture. And so here we end this meeting. Thank you very much.
Thank you very much.
Thank you. Thank you.